Now that we've looked at energy and Newton's laws, the next logical step is momentum. Momentum, I'm sure, is a word that you've heard before, and maybe you've even used it, but a lot of people misuse the term, so let me define it for you. It's very similar to kinetic energy. It's sort of like kinetic energy's evil twin, and it's simply a measure of how much stuff is in motion. In physics, the symbol for momentum is a rho, which looks like a sideways P. And the way that you calculate momentum is simply mass times velocity. So as a very simple example, if I had a 5 kilogram block just floating in space and it's going at 3 meters per second to the right, we would say that this object has a total momentum of 15 going to the right. Unlike kinetic energy, momentum has a direction associated with it as well, so we need to include the fact that it's 15 to the right. Or as another example, if you look at the green block, it's 6 kilograms and it's going 4 meters per second to the left, so we would just say that it has a momentum of 24 to the left. Or, as usual in physics, if you want to express direction, you could simply say it has a momentum of negative 24, because in physics, negatives just mean direction. Okay, so now that we know what momentum is, why do we care? Well, just like energy, we can use the idea of momentum to solve problems. And there's only one rule associated with momentum. And this rule is very similar to the rule that we saw with energy. It's a conservation rule, which means that the total amount that you have at the beginning of the problem had better equal the same number as the total amount that you have at the end. Momentum is conserved. A really simple way of saying it is the total momentum at the start of the problem had better equal the total momentum at the end. Or another way that you could write it. So here's what's cool. While the idea of momentum is kind of a complicated thing and it's really, really important for physics, the basic problems that we're going to start out with in momentum are actually very easy. So if the only idea is that the total momentum at the start equals the total momentum at the end, then all we have to do is look at every object at the beginning of the problem. So let's say we have a problem that has 3 or so objects. Then at the beginning of the problem, we just do mass of object 1 times velocity of object 1 plus mass of object 2 times velocity of object 2. We're just adding up the momentums, the right word is momenta, of every object at the beginning of the problem. And then when you add them all up at the end of the problem, that number had better be the same. Now, typically the masses aren't going to change very much in the problem. It's the velocities that are going to get messed around. So maybe you have one object that gets faster and another one that gets slower. But at the end of the problem, everything's going to balance out so that the total momentum remains unchanged. As a really basic problem, so you can see how momentum works in the real world, we've got two ice skaters, a 60 kilogram girl and a 90 kilogram girl, and they push off of each other on the ice. If the 60 kilogram girl ends up going 3 meters per second, what is the 90 kilogram girl's velocity? So for momentum problems, a really good first step is to just draw the thing out so that you can keep track of everything. It just prevents you from making mistakes. So this is a really simple situation. At the beginning of the problem, we've got the two skaters and they're just sitting there. And then at the end of the problem, the 60 kilogram girl is moving to the left at 3 meters per second, which means the 90 kilogram girl had better be moving to the right at some unknown velocity. And we know this because of Newton's third law, right? One person can't be pushed to the left without pushing something else to the right. Momentum conservation is just kind of another way of saying that Newton's laws are true. Okay, so there's only two objects involved here. So I've just got my simple little chart set up where we've got the momentum at the start, so mass of the first girl times her velocity plus mass of the second girl times her velocity, and then that had better be the same amount at the end. So let's throw the numbers in. So if I throw everything in, at the beginning of the problem, neither of the girls are moving, which means they have a starting momentum. The entire system begins with the momentum of 0. So the momentum at the end of the problem had better be the same. Well, if we look over here, at the end of the problem, the 60 kilogram girl has a velocity of -3, and the 90 kilogram girl, well, we don't know what her velocity is, but this had better still be true. The only way for the total momentum to be 0 at both the beginning and end of the problem is if the 90 kilogram girl gets a velocity of positive 2 meters per second.